Hello everyone, welcome back to another episode of Study Smart. In today's video, we are going to be talking about the power series, and under the power series, we'll be talking about the Frobenius equation. Right, the Frobenius equation. The Frobenius equation is one of the methods we use in writing a power series of an ODE. Right, we have several methods in terms of operating with power series. Alright, we have several methods in terms of operating with power series, and then firstly we have what is called the first method. We have what is called the Leibniz-Maclaurin series. We have the Frobenius equation. We have the Bessel, legendary polynomials, and what have you. Alright, so in the course of this video, we are going to be drilling on the Frobenius equation of the power series. Alright, how to use Frobenius equation to write a power series. Alright, so that's what we are going to be talking about now. Alright, so the Frobenius equation is an equation that has the expression of the kind a of x. Alright, so this is a of x y prime prime, because we are dealing with equation ODs to the second power. We are dealing with OD to the second power. Right, so this becomes a of x. The Frobenius equation has the expression of the kind a of x y prime prime plus b of x y prime plus c of x y equal to 0. Alright, so we can call this equation 1. Alright, so from equation 1 here, we've expressed this in Frobenius equation. This is an equation, alright? So this is the Frobenius equation. Alright, so from equation 1, if I divide this whole expression by the coefficient of the first term here, which is this. So if I divide the whole expression here by a of x, let me say divide equation 1 by a of x here, I'm going to be obtaining y prime prime, because this will go. I have plus b of x over a of x y prime, and I have my plus c of x over a of x y equal to 0. So we can call this equation 2. Right, so this is another form of expressing the Frobenius equation. Right, so the Frobenius expression can also be expressed in this form. Right, so from equation 2, we can deduce equation 2 by saying equation 2, let's say p of x at this point is equal to the coefficient of y prime, which is b of x over e of x. Right, so we can call this equation 3. Right, so similarly, we can, since we're giving here p, let's give the next one another alphabet. Let's say q of x. Q of x is equal to this whole expression, which is c of x over a of x. Right, so we can call this equation 4. Right, so you notice something here. Because b of x over a of x is the same thing as p of x, and then c of x, this is c. Right, so c of x over a of x is the same thing as having q of x. It means that from my equation 2, I can express equation 2 in another form in terms of p of x and q of x. So it means that I'm going to have, from equation 2 here, I'm going to have y prime prime, alright, plus b of x over q of x here is p of x. So I have p of x, alright, so I have my y prime here. So plus c of x over a of x here gives me q of x. So I'm going to be having q of x here then I have my y equal to 0. So we can call this equation 5. Or you notice that we deduced the Frobenius expression from this point down to this point, then down to this point. Right? So if you notice something here, we have P of x and then Q of x. What are P of x and what are Q of x and what are they used for? Right? So we can just say this is equation 3 and 4. Equation 3 and equation 4 denotes, or it is used to find what we call the ordinary points and the singular points. Right? So equation 3 and 4 denotes what we call the ordinary point, and what we call the singular point. Alright, so by singular point we mean regular and irregular point. So at this point we have regular, and irregular point. Alright, so that's what we use this P of x and this Q of x for. If you are given a differential equation, you have to check, because sometimes you can be given a differential equation without knowing the kind of method to use in solving for or looking for the power series of that equation. That's why we use Frobenius. Then when we use Frobenius here, it implies that Frobenius is always used when the point is a singular point. It's always used when the point is a singular point. Alright. After you've tested from this point, you follow the same process from the given equation you've gotten, or you are being given. You follow the same process, and then you get to this point. You test for your ordinary point or your singular point. If that function is an ordinary point, you don't use Frobenius equation, because if you use Frobenius equation when the given equation is at ordinary point, it is going to give you a 0, or you just continue solving without it. Alright, so that's how all these things work. Alright, so by ordinary point we mean that if P of x and A of x, Q of x are at ordinary points, it means that they are finite. Alright, it means that they are finite. So by ordinary point, we mean that P of x and Q of x are finite. What we mean by finite is where we have 0, 1, 2, 3, 4, 5, minus 1, minus 2, and all the rest. Alright. So when you find such kind of condition after you've tested and your P of x or your Q of x is giving you such numbers, that means it is an ordinary point. Alright. So by singular point, we mean that P of x and Q of x, if P of x and Q of x is giving you an infinite number, and that is if P of x and Q of x is the solution is giving you infinite, that means indeterminate. That means it implies that the expression is at singular point. So at singular point, it's what? Infinite. Alright, so we are going to be illustrating this thing with an example, so we can use the Frobenius equation or the Frobenius method to find the series expansion of that particular solution. Alright, so don't forget, you only use Frobenius method when the function is at singular point. When it is not at singular point, you don't use Frobenius equation or method. You don't use Frobenius method at ordinary point. What you use at ordinary point is what we call the Leibniz-Maclaurin series. You use the Leibniz-Maclaurin series for an ordinary point. When P of x and Q of x is giving you an ordinary point, you use Leibniz-Maclaurin series. But if the P of x and Q of x is giving you a singular point, you use Frobenius equation. you use Frobenius equation. So we are going to be taking an example very quickly to illustrate the point. Alright, so before I give this example, I forgot to say something. Alright, I forgot to give you the expression for the power series of the series expansion for Frobenius equation. Alright, so the series solution for Frobenius equation, series solution for this guy, for Frobenius equation, is y equal to summation n equal to 0 to infinity a subscript n x to power n plus r. Alright, so this is the series solution for Frobenius equation. Alright, so if you are being given a differential equation to a certain power, it means that this series solution, I'm going to differentiate it to the number of, or to the highest degree given in that equation. Alright, so you have to take note of this. Alright, so let us take an example. You can say find the series solution, find the series solution, find the series solution of we have 2x y prime prime. Right, so let me just turn this. This is 2x the square y over the x squared plus dy over dx plus y equal to 0. Right, so assuming we are not asked to use any method, we are just given a question like this: find the series solution of 2x the square y over dx squared plus dy over dx plus y equal to 0, and we don't know the kind of method to use. We test. Alright, so we test. So how do we test? Using the method I told you earlier. Firstly, let me change this form to a simpler term so we can be able to use it very well. Alright, so I'm going to be having 2x. Alright, so the square y over the x squared is also giving me the same thing as y prime prime. Alright, so I have plus dy over dx that gives me y prime. Then I have my plus y equal to 0. So this and this, they are the same thing. Alright, so they are the same thing. Alright, so following the rules I gave you, I told you that you are going to divide the whole expression by this guy. So if I do that, I'm going to be obtaining y prime prime plus 1 over 2x y prime plus 1 over 2x y equal to 0. Alright, equal to 0. Alright, so this is my a of x, b of x, and then c of x. Alright, so my a of x here is 2x, my b of x is 1. Alright, my c of x here is 1, my a of x here is what? 2x. Alright, so following the condition I gave you, I told you that when testing, you have p of x equal to a of x, this is b of x over a of x. Alright, so b of x over a of x is this guy here. So I'm going to have 1 over 2x. Alright, so for q of x equal to c of x over a of x. Alright, so it's going to give me, this is c of x over a of x here, which is 1 over 2x. Alright, so I told you that a point is said to be an ordinary point if p of x and q of x is giving you a finite solution when x is being substituted equal to 0. Note that x must be substituted equal to 0. So at x equal to 0, p of x and q of x, if it is giving you a finite number like 1, 0, minus 1, and all the rest of the values you have, it becomes an ordinary point. But if p of x and q of x at x equal to 0 is giving you an infinite solution, that means the point is a singular point. It means that if I substitute 0 to this point, I'm going to have 1 over 2 times 0, which is going to give me 1 over 0. Alright, so at this point, I'm going to have what? Indeterminate. If I press 1 over 0 in my calculator, I will have math error, which means indeterminate. And then here too, I will be having 1 over 2 times 0, which is 1 over what? 0, which is also going to give me what? Indeterminate. So from this point here, you know that this is an infinite solution. So I can use what? Frobenius what? Equation. I can use Frobenius method to find the series expansion of this. All right, I can use Frobenius equation to find the series expansion of this, but we are not going to be working with this guy. We are not going to be working with this guy. What are we going to do? What are we going to do when we have this kind of when we have an indeterminate solution for P of x and then Q of x? What are we going to do? All right, what are we going to do? We are not going to be working with this guy, but rather we are going to be converting the indeterminate function to a determinate function. We're going to be converting indeterminate function to a determinate function, meaning that I am going to convert this infinite function to a finite function. How am I going to do that? We have the standard way of writing for expressing this thing using in terms of testing for ordinary point and then singular point. All right, so take note that x minus x naught p of x. All right, so take note of this, and then we also have x minus x naught all squared, then q of x. Right, so this becomes for p of x, and then this becomes for what? Q of x. It means that at my x equal to 0, because I substituted x now, let us take x equal to what? Equivalent to what? X naught equal to 0. It means that I can use x equal to what? X naught to be what? Equal to 0. It means that this point here should be what? X naught. This point here should be what? X naught. So if I substitute x naught to be equal to 0, I'm going to be having this. So because I said we are not going to be working with this, we'll be working with this. All right. So it means that from my x naught, if I substitute x naught to 0 here, what am I going to be having? I will have x here. All right, so x minus x naught now becomes 0. So I have x. So what's my p of x? I know my p of x already. And what's my p of x? This is my p of x, which is what? 1 over 2x. So I have times 1 over 2x, which is going to give me what? 1 over 2. Because when this cancels this, I have 1 over 2, right? Which is going to give me what? 0.5. This is not an infinite value. Now we've converted it from what? From an indeterminate to what? Determinate. All right, secondly, for here too, I have x squared. All right, so this becomes what? 0, because x naught here becomes what? 0. So I have my q of x. And what's my q of x? Q of x is what? 1 over 2x. So I have times 1 over what? 2x. Right, so this is going to give me, when this cancels out this, I still have what? X over 2. So at x over 2, if I substitute 0 here, I'm going to have what? 0 over what? 2, which is going to give me what? 0. This is what? A determinate function, not an indeterminate function. All right, so what is the whole idea of everything I did here? The whole idea of everything I did here is to know when to use a specific method in solving a given differential equation when it is being given without specifying any method to use. Don't forget, we have different kind of method of finding the power series of any differential equation. Like I said earlier, we have the Leibniz-Maclaurin series, we have the Frobenius equation, we have the Bessel equation, the legendary polynomials, and all the rest. Right, so if it is not being specified that use this particular method, how do you know the right method to use? This is what you will do. Don't forget, at singular point, use what? Frobenius series. At ordinary point, use what? Leibniz-Maclaurin series. But in our subsequent videos, we are going to be drilling or maybe discussing on the what? Leibniz-Maclaurin series. Right, so we are going to be solving this example. What we just did now is to know the kind of method we are going to use in solving this example. So we have known that this is a singular point and we are going to be using what? Frobenius equation. Frobenius method to do what? Solve this differential equation. And I told you that the series solution for what? Frobenius equation is this. Alright, is this. So we are going to record this. We are going to record that the series solution for Frobenius equation is what? Y equal to what? Summation n equal to 0 to infinity. I have a subscript n, then I have x to power what? N plus what? R. So that is the series solution for what? Frobenius what? Equation. Alright, so I have here the highest power of y is what? 2. So it means I'm going to differentiate this series solution what? 2 times. So I'm going to find y prime from here. I have summation n equal to 0. Summation n equal to 0 to infinity. I have an. Alright, so n plus r, x to power what? n plus r minus what 1. So what we did there was differentiation. Pick the whole of these things, just like when we have an expression um x to power n, alright, x to power n. It means that when differentiating this whole stuff, I'm going to move this n here to the front, and I have x here, and I reduce the n by 1. That's the differential of this. That's what we just did here. Our n here is the whole of this. We multiply it by the expression, reduce it by 1. That's how we got this. Right, so don't get it confused. So we've just gotten y prime. So let's get y prime prime now. So in getting y prime prime of this expression, it means that we are going to differentiate y prime again. So we are going to have summation n equal to 0 to infinity of an. All right, I have n plus r, and I have n plus r minus 1, and I have what? X to power n plus r minus 1 minus 1. Alright, so I'm going to reduce this again by 1. I'm going to multiply this first by this expression, then reduce it again by 1. So minus 1 here will give you what? Minus 2. So I'm going to change this to minus 2. Alright, so when you've gotten up to this point, what next are you going to do? What next are you going to do? So what you are going to do after this point is to substitute the value of y and its differential to this particular equation here. So in doing that, what we are going to be having is let's just do that over here. Alright, so in doing that, what we are going to be having is 2x. I have 2x. Alright, so y prime prime is this. So I will carry the whole of this and I substitute it there to obtain summation n equal to 0 to infinity. Alright, so I have an into n plus r. I have an plus r minus 1. I have x to power n plus r minus 2. Alright, so that's what I have. This in a bracket. Alright, so this in a bracket. Alright, so I have y prime, which is this. So I'm going to have plus y prime, which is the whole of this, summation n equal to 0 to infinity. I have a subscript n plus r, then I have x to power n plus r minus 1. Right, so that's for this. Then lastly, I have y, which is this. Then plus y. I have summation n equal to 0 to infinity of a subscript n x to power n plus r all equal to what? 0. It means that we just deduce, or we just change this equation, this differential equation, in terms of series equation. It's not a series equation now. Alright, so we just differentiated. We record the series solution for Frobenius equation, which is this, and we differentiated it twice because the highest power here is 2. And then after that, we substituted its differential and the value of y, of the expression of y, to this particular equation to obtain this. And after all, you equate it to 0. So what next are we going to do when we've gotten up to this point? So when we've gotten up to this point, you can notice I will have x here. So in performing indices, this can go. Alright, this can go. In performing indices, this can go. It means that from here, I'm going to have what? 2. Right, so let me just draw a line here so we don't get it confused. So we are solving it again. So from here, I have x and I have x here. It means that this becomes what? 2 summation n equal to 0 to infinity. Alright, I have my an into n plus r. I have n plus r minus 1. Then this is x here to power 1. This is to power 1, and this is x. I have x. I pick one of the x, then I'm going to add up the exponent, that's the powers. So I'm going to have n plus r. Right, so this becomes minus 2. Don't forget you are adding up the power. So here becomes 1 plus 1. So it becomes minus 2 plus 1. So minus 2 plus 1 now gives me minus 1. Right, so it becomes minus 1. Right, so that's for this. So every other thing here remains the same because there is no other x here to deduce it with. So I'm still going to have plus summation n equal to 0 to infinity. I have this an to power n plus r, x to power n plus r minus 1, and then I have plus summation n equal to 0 to infinity an x to power n plus r all equal to what? 0. Alright, so all equal to 0. So this is our new expression, and this is the expression we are going to be what? Working with. This is the expression we are going to be what? Working with. Alright, so from this point here, you observe something here. You observe something here. I have x to power n plus, this is plus here. I have x to power n plus r minus 1 here. I also have x to power n plus, alright, r minus 1. It means that I can actually factor out these two terms. Alright, I can factor out this term and this term because they have what? The same word, summation. I have the summation here, n equal to 0 to infinity. I have also n equal to 0 to infinity, and the powers are what? The same, so I can factor them out. Let me just factor it out over here. I'm going to have, let me drop summation n equal to 0 to infinity, and then let me open up a bracket, and then here I have, there is still 2. Right, so there is 2. You notice here too I have an and an. Right, so we are factoring out what is common in the two terms. Right, so here is n plus r. There is no minus 1 here, so that means we are going to treat this one as a separate term, and then treat these two as a separate term because they can be factored out. We have the same powers of what? X. We have the same summation, and we have a of n. Alright, we have an rather, a subscript n. It means that I have 2. Before then, I have an here, so I can factor it out, an. Then I am going to be having, then my 2 here, 2 times this expression, n plus r. I have n plus r. I also have n plus r minus 1. N plus r minus 1. And then I have this. I also have, this becomes plus, right? So I'm using plus. So I have this because we factor this out. We factored this out, so we are not going to be including it there again. So I have n plus r. So I have n plus r. Right, so this is what I have. Outside, I'm going to have the powers now. Xn plus r because they are having the same power. So this is xn plus r minus 1. Right, so that's for this 2. Right, so what we just did there, we factored the common terms out. These and these are common, these and these are common, and then these and these are common, so we factored it out. And then we have this plus summation n equal to 0 to infinity, then an x to power n plus r, I still have equal to 0. Right, so the major idea, the whole idea of, in this Frobenius equation, we are going to get two equations. We are going to be getting two equations. One of the equation, we are going to be getting one, what we call the indicial equation. And then secondly, we are going to be getting what we call the recurrence relation. That is the recurrence relation. Alright, we are going to be getting the indicial equation and then the recurrence what? Relation. In the indicial equation, we are going to be having two values of what? We are going to be having two values of r. It's just like having a quadratic equation, then you are solving for two roots. Then it's from the recurrence relation that we are going to look for. Don't forget, in this series, we are looking for a naught, a1, a2, a3, a4, as the case may be. And the whole of this thing should be expressed in terms of a naught and what? A1, depending on the kind of initial equation and the root you've gotten. That's just what we are doing here. That's just the major idea, what we are doing here. is to express this whole stuff in terms of this. In terms of this, we are going to be having from here, from this our whole series equation here, we are going to be creating from the whole series equation the initial equation, and we are going to be creating again from this whole series equation the recurrence relation. So in Frobenius series, this is more like the most tricky part of it. This is more like the most tricky one. Once you've gotten up to this point, it becomes trickish. At the same time, simple, only if you understand. Alright, only if you understand what you are doing. So at this point, you need to pay optimum attention, because at this point there is always confusion. There's always confusion at this point, how to get your initial equation and how to get your recurrence relation. So I'm going to break everything down here, so that when you see Frobenius equations anywhere, or maybe an ODE somewhere else, you can use Frobenius equation to use to tackle it when it is a singular point. Right, so how are we going to get our initial equation? Firstly, we need to get the initial equation. We need to get the initial equation. How do we get the initial equation? From the first term, let's leave the last term. This is first term, this is second term. Right, so this is first term, the whole of this, first term, this is second term. So, but let's leave the second term first. Focus on the first term. So now from the first term, let us substitute n equal to 0 in this expression here. This expression enclosed inside this bracket. It means that I'm not going to be touching this and then every other thing here. So this is my major focus, so that I can be able to get my initial equation. Right, so I'm going to substitute. Alright, so the major idea, let me just tell you something. Just in case of it is not like this. How do you get your initial equation? You are going to get your initial equation from the lowest power of x. That's the simple way to understand this. From the lowest power of x. Now we have two powers of x here. We have x. The first one, x is what? N plus what? R. That's the first power. And the second power is what? X raised to power what? N plus what? R minus what? 1. These are the two powers of x we have. Let us assume that n plus r is equal to 4. Let's just assume it like that, so that we know our lowest power of x here. If n plus r is equal to 4, it means that anywhere I see n plus r here, I put 4. So here will be what? X to power what? 4. While here will be what? X to power what? 4 what? Minus 1, which is what? X to power what? 3. It means that the lowest power of x here is this. The lowest power of x here is what? This. So it's from this lowest power of x I'm going to get my initial equation from. So take note of that. You get your initial equation from the lowest power of x, which is this point. Here is the lowest power of x. So this is where I'm getting my initial equation from. You get your initial equation from the lowest power of x. Take note of that. The lowest power of x, you get your initial equation from it. So I'm going to substitute here. I'm going to substitute n equal to 0 in the first term, because it is the first term that has the lowest power of what? X. So in the first term. So if I do that, what am I going to have? I'm going to be having summation. Let me do that down here. I'm going to be having summation n equal to 0 to infinity a of n. Right, so a of n here, a of n, I have into, right, I have 2 into, anywhere I see n here, I add what? 0. So this becomes 0 plus what? R. Alright, so this becomes here, this point, 0. So this is 0 plus what? R minus 1. And then plus, n here is 0. So I put 0 plus what? R. Then I have my what? I have my x to power what? N plus R minus 1. Like I said earlier, this is the only part what? Affected. Substitute n equal to 0 to this, so I can be able to get my what? Initial equation. So when I do this, if I open up this bracket, I'm going to have summation n equal to 0 to infinity of what? A of n, alright, um, I'm going to have, this becomes 0 plus arrow gives you what? Arrow. So arrow times what? 2 here gives you what? 2 arrow. So this is 2 arrow. Alright, so 0 plus this gives you arrow minus 1. So 0 plus 1 here, 0 plus arrow here gives you arrow. I'm still left with arrow minus 1. So that becomes what? Arrow minus 1. So I'm left here with plus arrow. Alright, so I have outside x to power n plus arrow minus 1. Alright, so from here I'm getting my initial equation already. Alright, so let me just pull out this whole stuff. Don't forget this is equal to 0. This is equal to 0. Alright, so I'm going to, the major interest here is this. That's the major interest. Understand the fact. You get your initial equation from the lowest power of x, which we did here, and then you're going to substitute n equal to 0 to that point where you have the lowest power of x. And this is the point where we have the lowest power of x. And I told you that our major concentration is what? This point. So we're going to substitute n equal to 0 to this point. And when we did that, this is what we got, and then we arrived at this point here. So we are going to pick out this point to bring it outside. If we bring it outside, we are going to be having 2 arrow into arrow minus 1 plus arrow equated to 0. Alright, equated to 0. Then 2 arrow times arrow gives you what? 2 arrow squared. 2 arrow times minus 1 gives you what? Minus 2 arrow. Then I have plus arrow equal to 0. Alright, so I'm still left with 2 arrow squared. Alright, so minus 2 arrow plus arrow gives me what? Minus arrow. So this gives me what? Minus arrow equal to 0. Alright, so this is factorizable. Arrow is here, arrow is here. So I can pick out one arrow outside. So I have arrow into, arrow cancel arrow here gives me what? 2 arrow. Arrow cancels arrow here gives me what? Minus 1 equal to what? 0. Alright, so this becomes my what? Initial what? Equation. I can pick this thing now and then rewrite it inside this point here to get my, this is now my initial equation. This is my initial equation. But to make it more unique and more sweet, you can just bring it back here to get summation n equal to 0. Alright, an into this whole expression now. I'm going to have what? 2 arrow. Alright, sorry. This is arrow into 2 arrow, 2 arrow, alright, 2 arrow minus 1, minus 1. Then I have outside x to power what? N plus arrow minus 1 equal to 0. Alright, so this becomes my what? Initial equation. Initial equation. I can use this, I can use this. Alright, so I just did it in this form so that to look sweet. Alright, so this becomes my initial equation. This thing inside here becomes my initial equation. So I can call this one equation what? Equation, let me use equation 3. Equation 3. Right, so let me use equation 3 there. So that is equation 3 now becomes my initial equation. Equation 3 becomes my what? Equation 3 is the what? Initial equation, which is what? This. Let me use this one here. Let me just remove it here. This is equal to 0. Let's call here equation 3. And let's use here as equation 3. Which is what? This. So summation n equal to 0 to infinity of an, alright, arrow into 2 arrow minus 1, alright. Outside I have x to power n plus arrow minus 1. So this becomes my initial equation. So I'm going to keep this in mind. Initial equation. Keep this in mind. I'm going to use it. Keep it in mind. We are going to use it. If possible, let's just go further to look for um to look for the roots of the values of r. Right, so we'll just do it the same time in getting the recurrent relation. But just know that this is your initial what? Equation. This is your initial equation. And from your initial equation, you will get your first recurrent relation. And then you will get another recurrent relation from the last term. You know that we have not touched the last term yet. We have not touched the last term yet. We've always been dealing with the what? The first term. And then now we want to touch this last term. And then we want to touch this again. Listen very attentive. We'll touch this one and then we'll touch this one. We're going to touch this one and then touch this one so that we are going to get our recurrence relation. All right, we're going to get our recurrence relation. All right, so let me use here. All right, so from this point, this becomes our initial equation, and then this becomes the last term. This becomes the last term. So we are going to be getting our first recurrence relation from this initial equation, and then we'll get another recurrent relation from this last term. Then we'll get the general recurrence equation, general recurrence relation. All right, so I said earlier that if I want to get my recurrent relation from this initial equation, I need just two things. All right, I need just two things. I need to substitute r equal to 1, sorry, n equal to 1 and n equal to n minus 1. All right, so where I will substitute n equal to 1 is different from where I'm going to substitute n equal to n minus 1. All right, I'm going to substitute n equal to 1 to the initial equation, that's the series of the initial equation. Then I'm going to substitute n equal to n minus 1 here to the last term. Right, so I will substitute n equal to 1 to the series solution of this. It means that I'm only substituting n equal to 1 to this series here. Then for arrow, anywhere I see arrow, I add n to it. So it means that my summation from n, instead of 0 now, I'm going to have what? 1. So here becomes 1 to infinity. Then I have an, all right, into, so anywhere I see arrow, I'm going to add n. So here becomes arrow plus n. All right, so I have 2. I still have arrow, add n. All right, so I have minus 1. And this becomes our first recurrence relation. All right, this becomes our first recurrence relation. You note something here, the power was not touched because we need to get a similar power and a similar summation so that we can be able to factor them out and then get our recurrent relation and then see how we can bring it out and then solve for the series. All right, so if you check where here, I have n plus r minus 1, and for the last term here, I have n plus r. So if you check very well here, the only thing missing from here is what? Minus 1. So I need to assume my values in such a way that it will give me what? The similar what? Powers of x here. The similar powers of x. And the only way I can achieve that is by substituting n equal to 1 in this summation and then substitute n equal to n minus 1. All right, n equal to n minus 1 to this last term here. All right, so that's what it means here. That's what it means. I'm going to substitute n equal to 1 to the initial equation here. And this n equal to 1 is only going for the summation here. All right, so if you check very well, this is from summation of n equal to 0 to infinity, it changes to what? Summation of n equal to 1 to infinity. It means that the n was only substituted what? At the summation here. Then you watch secondly, what I did also was inside this initial equation, anywhere I'm seeing arrow here, I add n to it. Anywhere I'm seeing arrow here, I add n to it. So this becomes a subscript n times arrow, add n. All right, bracket 2 times arrow. Inside the arrow, you add n to it, minus 1. Then I have this. All right, so that's my first recurrent what? Relation. Then for the second recurrence relation, I'm going to substitute n equal to n minus 1 to this last term. Alright, so substitute n equal to n minus 1 to the last term. So if I substitute n equal to what? N minus 1. I'm going to substitute it to what? To this last term. It means that I'll be having summation n. Here becomes what? N minus 1. So it becomes n minus 1 equal to 0 to infinity. Of course, n minus 1, it can be same thing as what? N equal to 1. Because by the time minus 1 shifts or crosses the equal to sign, it changes to plus. I will change that to n equal to what? 1. Alright, so I have a subscript n, of course what? N minus 1. So it becomes what? N minus 1. Alright, so x to power n. Substitute to what? N minus 1. So here becomes n minus 1 plus r. Right, so of course I can write this thing as what? N plus r minus 1. So it's also the same thing. So this becomes what? N plus r minus 1. So if you check very well, this term here and this term here, they have the same summation and then the same powers. They have the same summation and the same power. It means that I'm going to add them, then factor out the summation and then factor out this. So if I do that, what I'm going to have is, I'm going to be having this term here. I have summation n equal to 1 to infinity. Alright, summation n equal to 1 to infinity of an, then r plus n into 2 into r plus n bracket close minus 1. Alright, so plus, so this becomes plus. I'm adding it to this, so here becomes plus. Alright, plus, because the sign here is carrying what? Plus, so it becomes plus. And I have this a subscript n minus 1, then all multiplied by x to power what? N plus r minus 1. N plus r minus 1. So this is what I have. This is what I have. Right, so this is for this, and then this is for this here. It also means that I can write this as same as summation n equal to 1 to infinity of r plus n, alright, into 2 n plus r plus r plus n, alright, minus 1. Then this multiplied by an, alright, plus an minus 1. An minus 1, all multiplied by this power, x to power n plus r minus 1. Right, so this is it. And this becomes our what? Recurrent relation. Our recurrent relation. So we can just come here and call here equation what? Equation 4. Alright, so equation 4 is the recurrent relation. Alright, so we are going to be working with equation 4 as the recurrent what? Relation. Alright, so from that recurrent relation, I don't need much things inside. What I need is just this. Thing inside the bracket. So I'm going to pull the whole of this thing out, then I'm going to work with it. What I have here is r plus n. I have r plus n multiplied by 2, that is r plus n into 2 into r plus n minus 1. Alright, this is in brackets an, then plus an minus 1, equate it to 0. Alright, so this is equal to 0. This is equal to 0 here. So what I'm going to do from here, I'm going to make an the subject of the formula. If I make an the subject of the formula, I'm going to be having an equal to, this one will move over to this side, becomes minus an minus 1 over, divided by this, I have arrow plus n, arrow plus n, 2 into arrow plus n, minus 1, minus 1, all right, minus 1. This is what I have. Minus 1. This is what I have. All right, so we are going to be using this to get our series solution. All right, don't forget that our major aim here is to get the value of what? A1, A2, A3. Then we are going to express them in terms of what? A0. All right, we express them in terms of A0 and A1. All right, depending on the values of arrow we are getting from our initial equation. Depending on the values of arrows we are getting from an initial equation. All right, so this is what we are going to be working with. So we are going to keep this thing one side and then we'll come back to it later. All right, so let's drop this thing and go back to our initial equation. All right, so this is the recurrence relation we are working with here. And then from this our initial equation here, we need to get the value of arrow. We need to get the value of arrow. So what I need from this recurrence, initial equation, what I just need from the initial equation is this. So I'm going to pull out this, then equate it to 0. All right, equate it to 0. So this becomes arrow into 2 arrow minus 1, equate it to 0. I need the values of arrow. I need the values of arrow. So what I just need is this. So I pulled it out, equate it to 0. So this becomes, remember, when I have A into A plus B, it implies that A equated to 0. It implies that A is equal to 0 or A plus B is equal to 0. So I'm going to generalize this by applying the same idea here. So if I do so, I'm going to be having arrow equal to 0 or maybe and this becomes arrow equal to what? 1 over 2. All right, so if you perform your this becomes, from this inside bracket, r is equal to 0, we are left with this, right? So it becomes 2 arrow minus 1 equal to 0. If this crosses this equal to side, becomes 2 arrow equal to 1. Divide both sides by 2. All right, so I have r equal to 1 over 2. All right, so this is why I have this. All right, so this becomes my value for what? The initial equation, the values of r. So I'm going to be working with the values of r for this guy here, for this guy here. So what am I going to do? I'm going to give each of these cases. Let's say this is case 1 and this is case 2. And I'm going to work with case 1 and case 2. I'm going to work with case 1 and case 2. All right. So now, for case 1, all right, for case 1, I have r equal to 0. For case 1, I have r equal to 0. So I'm going to record this equation, record this initial equation, recurrence relation. I'm going to record this recurrence relation that A subscript n equal to minus A subscript n minus 1 over arrow plus n, all right, into 2 into arrow plus n minus 1, bracket close. All right, so what this means is that from this recurrence relation, anywhere, this is for case 1, anywhere I see arrow, I'll put 0 because r is equal to 0 for case 1. All right, so if I do so here, I'm going to be having, I'll just do the substitution here at once. I'll do the substitution here at once. If I put 0 here, from this denominator, I'm working with the denominator now. All right, so this is r equal to 0. This becomes what? Arrow here becomes what? Here becomes 0 plus n. All right, we have 2 into 0. 0 plus what? N. All right, minus 1. So it means that I'm going to write this. I'm going to rewrite this. So if I do so, I'm going to have 0 plus 0. 0 plus n here is giving me n. So it means that here will give me n. All right, so I'll change arrow plus 1 This r plus 1, I'll change it to what? N. So because 0 plus n here gives me what? N. So r plus n gives me what? N, because here will be what? 0. I'll change that to n. So here becomes n. So I have 0 plus n here gives me what? N. So 2 times n gives me what? 2n. Then minus 1. So I'm going to be having multiplied by what? 2n minus 1. So this is what I have. So this is what I have for case 1. For case 1, this for case 1. Then for case 2, where r is equal to 1 over 2, I'm still going to do the same thing. I did there. I will recall an, all right, equal to minus an minus 1 over what I had there was this r plus n, all right, into r plus n into, all right, so this becomes 2 into r plus n, all right, minus 1. So where r is equal to 1 over 2, I'm going to substitute 1 over 2 into this expression. All right, so from here, I'm going to substitute r equal to 1 over 2. So this expression becomes an into minus an minus 1 over r here becomes what? 1 over 2. So this becomes 1 over 2, then plus n, all right, into 2 into what? 1 over 2 plus n, all right, minus 1, bracket close. All right, so this is the expression we are going to have. This is the expression we are going to have. Then from this point, an will be equal to minus an minus 1 over. All right, so from this denominator, if you perform a factorization here, you're going to be having n into 1 plus 2n. All right, so 1 plus 2n. So we have this now for case 1. All right, we have this now for case 1, and we have this now for case 2. So I'm going to be working with this 2 now. This becomes the solution. This becomes the expression where we are going to be having the series expansion. That's the power series of the what? The given question. For case 1, where r is equal to what? 0. Let's bring back this. We have what? An equal to minus an minus 1 all over n into 2n minus 1. Alright, so this for case 1. And then let's also do that for case 2 here. Case 2, when r is equal to half of this expression, an equal to what? Minus an minus 1 all over n into 1 plus 2n. Alright, so I'm going to be working with these two expressions. Alright, so what I'm going to do now is I'm going to substitute n equal to 1 to any number you want. Maybe n equal to 1, n equal to 2, n equal to 3, as many as you want to what? Expand. But in the course of this video, I'm just going to do for n equal to 1 and n equal to 2. Then we'll write the series solution of it. That's all. Alright, so this becomes, alright, so for case 1, let us substitute n equal to 1. So if I substitute n equal to 1 to this expression, I'm going to be having a1 equal to minus a1 minus 1, which becomes what? A naught. Alright, becomes n here what? 1 into 2 times what? 1 minus 1. So this becomes what? Minus a. 1 minus 1 gives me what? A naught over 2 times 1 is what? 2. 2 times 1 is 2. 2 minus 1 is what? 1. Right, so 2 times 1 is 2. 2 minus 1 is what? 1. And then 1 times 1 is what? 1. Alright, so this becomes what? A1 is equal to what? Minus what? A naught. So this is what I have. Alright, so let me do A2. Sorry. If I substitute n equal to 2, I'm going to have A2 equal to Here becomes minus a into what? 2 minus 1 all over. Here becomes what? 2 into, I have 2 into 2 minus 1. Right, so n here for n equal to 2 is 2. Here 2. This point here 2. So I'm going to be having minus a what? A1 minus a1 all over. I have 2 times 2 here gives me what? 4. 4 minus 1 gives me what? 3. 3 times 2 gives me what? 6. So I'm going to be having minus a1 over what? 6, which is going to be equal to what? A1 here, we know A1 here to be what? Minus 1. So it means that anywhere I see A1, I substitute what? Minus 1. So this becomes minus into A1, which is minus 1, minus A0, sorry, over 6. A0 over 6, because A1 here is what? Minus A0. So it means that anywhere I see A1, I substitute what? Minus what? A0. So minus minus here is what? Plus. So this becomes what? A0 over 6. Therefore, A2 is equal to what? A0 over what? 6. Right, so I said I'm just going to be doing for two, I'm going to be doing for n equal to 1 and n equal to 2. N equal to 1 and n equal to 2. So let's do the same thing for here. Let's substitute n equal to 1 to this case here. I'm going to be having a1 equal to minus a into what? 1 minus 1 over 1 into 1 plus what? 2 times what? 1. So if I do that, I'm going to be having minus a 1 minus 1 0, that's minus a naught over, this becomes what? 2 times 1, which is 2, which is 2. 2 plus 1 is what? 3. Then 3 times 1 gives me what? 3. So this becomes 3 for a1. Then if I substitute n equal to 2, I'm going to be having what? A2 equal to what? Minus a what? 2 minus 1 all over. That becomes what? 2 into 1 plus what? 2 times what? 2, which becomes minus a 2 minus 1 gives me what? 1 all over. Right, so it becomes 2 times 2 is what? 4. 4 plus 1 gives me what? 5. 5 times 2 gives me what? 10. So that becomes what? 10. Alright, so I know my A1 from here. I know my A1 from here. So my A1 is what? Minus what? A naught. Minus A naught. Minus A naught. So my A2 becomes what? Minus into A1 here is what? Minus A naught over 3. Minus A naught over 3. So it becomes minus A naught over 3. Alright, minus A naught over 3. All divided by what? All divided by what? 10. All divided by 10 over 10 over 10. So it means that this becomes equal to, all right, which becomes what? A2 becomes what? A naught over what? 30. So we've known this is our this thing series. So we are going to be combining this series for case 1 and what? Case 2. All right, for case 1 series, the expansion power series for case 1, power series for case 1, where r equal to 0. So we are going to be having what? Recall that y will be equal to what? A naught plus a1x plus a2x squared plus a3x cubed continues to the form of what? A n x to power what? N. So we are going to be using this. We are going to be the general solution of this will now be y equal to y1 plus what? Y2. Because we have two cases, we are going to be looking for what? The two cases there. Alright, so for y1, for case 1, alright, so we have a naught. Remember, or don't forget that in this whole expression that we are doing, a naught must not be equal to what? 0. Even from this series expansion, if you check very well, we started from what? A1, A2, and all the rest. But just bear it in mind that what? A naught is not what? Equal to what? 0. So it means that I'm going to be having what? A naught plus, alright, plus my A1 here for this first case. I'm dealing with this first case now. My A1 there becomes what? A1 becomes what? Minus A naught. Minus A naught. So this plus changes to minus. I have minus A naught what? X. Alright. So I have what? N equal to 2. I have A2. So it becomes what? My A2 here becomes what? A naught over 6. A naught over 6. So A2 plus A naught over 6. Then I have what? X to power what? 2. That's my Y1. Then for case 2, for case 2, where R is equal to 1 over 2, my Y2 now becomes equal to A naught. Remember, A naught is not equal to what? 0. A naught is not equal to what? 0. A naught what? Then I have for case 2, my A1 here becomes what? Minus A naught over 3. Minus A naught over 3. So A1 becomes minus A naught over 3. And I have X. Alright, so I have A2X squared. My A2 here becomes what? A naught over 30. A naught over 30. So this becomes plus A naught over 30 x to power what? 2. X to power 2. So we have for the two cases this, and we have what? This. This is for case 1 and this is for case 2. So from the general solution, we said y is equal to what? Y1 plus what? Y2. It means that I'm going to sum up this and this to get our what? General what? Solution. That is what? The series expansion, the power series of the given equation. If I do that, I'm going to be having first recall that y is equal to what? Y1 plus what? Y2. Alright, so my Y1 becomes what? The whole of this expression, which is what? Y now becomes what? Y1 becomes what? A naught minus A naught X plus A naught what? Over 6. Alright, X squared. Alright, so that's where it ended. This is Y1. Then plus my Y2 becomes this, which is what? A naught minus A naught over what? 3x. Then plus A naught over what? 30 x squared. And this becomes my what? My Y2. So you can see that A naught is common for both cases here. So I can decide to factor out A naught. So this becomes what? Y should be equal to, so A naught is common here. I'm going to be having what? A naught. Alright, I'm going to be having what? A naught. This becomes into A naught here becomes what? 1. And I have minus. I'm left with x. Alright, plus x squared over what? 6. Alright, so that's for this. Then I have plus, I have another A naught into, this becomes 1 minus x over 3. Then I have plus x squared over 30. X squared over 30. And this becomes the final answer, and this becomes the final answer of the problem, which is the what? The power series of the given differential equation that we what? That we were given to what? To solve for. Alright, so this becomes the what? The final what? Solution. This becomes the final solution. The idea here is very simple. Given a differential equation, you recall the series expansion for Frobenius equation if Frobenius equation is valid for that differential equation. Meaning that if Frobenius equation is valid, it is a singular point. But if Frobenius equation is not valid, means that it is not a singular point, it is an ordinary point. So by ordinary point, you use the Leibniz-Maclaurin series. By singular point, you use what? Frobenius method. Recall the series expansion for Frobenius equation differentiating the number of or the highest degree of the equation given, then substitute it to the equation. After you've done that, you look for your initial and then recurrence equation. Your initial equation, you look for it, look for the values of n, the values of r in the initial equation, and then get your recurrence equation, your first recurrence equation from the initial equation, and then get your second recurrence equation from the last term, and then get your general recurrence relation from by summing the recurrence relation gotten from the initial equation and the recurrence relation gotten from the last term.